everyone. Today, we have the pleasure to have Professor Thomas Helweg here speaking at the CNANO seminar, and I will give you a profile of Professor Helweg. He worked by now at the University of Bielefeld, but he was also in Berlin and in German at the Bayreuth University. He was a member of the scientific committee of the Laboratoire Léon in France and was chairperson of Fachgruppe Chemie in Bayreuth. He was also a member of the Desi Petra working in soft matter in German, and he is working as a member of the editorial board of, for instance, ACS Omega is a very good journal from ACS, and he is also member of synchrotron committees, and he is chief editor of the journal Frontiers in Soft Matter, working a lot in colloid and polymer science. He has a lot of very important publications, and most of all are related to his field of work, which is soft matter, colloids, and nanoscience. Professor Helweg has a career since 20 years working in these subjects, and his H index is around 50. So be welcome, Professor Helweg, with your talk. Thank you for attending our invitation.
Yeah, Nadia, thanks for the kind introduction. Do you hear me? I hope so, at least. Okay, so first of all, the title of my talk today is Structure of Smart Acrylamide-Based Core Shell Microgels as seen by small angle neutron scattering and super resolution microscopy. As Nadia already mentioned, I'm from Bielefeld University, and I'm a member of the Bielefeld Institute of Nanoscience, where the buildings are shown here on the right. Bielefeld, for those who have not yet been in Bielefeld, is located halfway between Dortmund and Hanover. And we have some nice medieval buildings in the city center. This is the old market. This is an old factory from 19th century, and also some nice rocks in the landscape around Bielefeld can be visited. So it's a very nice place. And besides these sites, we have the university. This is the university main building, which is at the moment under heavy reconstruction. It has to be entirely renovated. And this building is, as far as I know, the largest university building in Europe, at least, with about 230,000 square meters of usable surface. Besides the renovation works going on here in this main building, we have here the works going on to build up our new medical school. And so the university is steadily growing and has at the moment about 24,000 students. And in the last rankings of Times Higher Education, we were ranked among the young universities number 19 worldwide. But this is, of course, not the topic of my talk. I will talk about smart microgels today. First of all, I will talk a little bit about about properties in general and possible applications of these materials. Then I will talk in the second part about response kinetics of these materials, because this is why they are called smart. They can respond to external stimuli. And we have investigated this by pressure jump experiments using small angle neutron scattering. The third part is devoted to the main topic of my talk, core shell microgels. And at the end, I will give a short conclusion and outlook. And now let's come to properties and applications of these systems. So first of all, hydrogels are, of course, very important, since, in fact, all humans are a kind of hydrogel. So if you look at the cytoskeleton, that's nothing else than a hydrogel. And if we are lucky, we are smart. So also humans are kind of smart hydrogel. But in Bielefeld, we have another important kind of hydrogel. This is shown here. I guess this is also sold in Brazil. So this is, a gelatin-based jelly. And Oetker company is located in Bielefeld, and they sell it worldwide. Okay, but now let's come to the thermoresponsive or smart microgels. They are colloidal particles with internal gel-like structure, and they can be swollen by a solvent, and they react on external stimuli by a change in volume. And this is shown here. On the right side, you see the swollen particles, and when you heat them up, they shrink, and when you cool down again, they swell again. So this is a reversible transition, which is driven by a so-called microphase separation, and we call this transition volume phase transition of the particles. Here you see a plot of the radius versus temperature, and this is hydrodynamic radius as measured by dynamic lights or by photon correlation spectroscopy, and you see the radius goes down drastically at this so-called volume phase transition temperature. And the transition temperature can be modified by copolymerization with other comonomers, and you can also make these particles responsive with respect to pH, or they are also responsive to ionic strength and pressure. They were first synthesized by Bob Pelton and his PhD student Shibante in 1986 already. And the interesting thing is, as already mentioned, the volume phase transition. And when you change the monomer, then you get different transition temperatures. So here you see the normalized hydrodynamic radius versus temperature for 3 different acrylamides. This is NNPAM, then of course the best studied NIPAM and NIPMAM. And you see that they have different transition temperatures, and you can find, of course, much more monomers which are thermosensitive in water, and a list is shown here. So here you have, of course, NIPAM, the most well-known one. This is NIPMAM. This is NNPAM. This is NNMAM, and NIPMEAM, and NNPNEAM. Oh God, the names become a bit unhandy at the end. But you can also make similar systems using glycidyl ethers, which are also thermoresponsive. In fact, all polymers which exhibit in solution, in aqueous solution, an LCST, can be used to make such particles. The particles are colloidal, as I already mentioned, and they are stable in solution due to surface charges induced by the monomer, by the initiator we use in the synthesis. The synthesis is a so-called precipitation polymerization. As mentioned, this was introduced by Pelton and Shibante. Okay, when we want to look at these systems, one possibility is, of course, using small angle scattering. And here I just wanted to show you a recent example for characterization. Here we synthesize the particles in a flow reactor, and then in the flowing system we study the sex pattern, the small angle X-ray scattering pattern of the particles. Here you see a typical form factor, and the good thing about this is that we can change the flow rate in this reactor, and we can in situ study the particles growing, and time resolution is achieved by changing the flow rate or by scanning this capillary here, which is in the X-ray beam. This is done in this case with an in-house X-ray machine, but of course when you want to reduce the volume needed, then you go for a synchrotron experiment. Another issue in these systems is, of course, the description of the swelling behavior. There was a classical paper by Flory and Reyna already from 1944, and they introduced an equation consisting of an elastic contribution and a mixing contribution, and both contributions together are balanced when the system is in swelling equilibrium. So you have the osmotic pressure balanced by these two contributions. And for a copolymer system, you would need 2 times the chi parameter. So we have 2 different chi parameters. If you would just go for a homopolymer system, you can remove one of these. Okay, but the problem is, in fact, this chi parameter, the Flory-Huggins interaction parameter, because it can be modeled only for very few cases and was successfully used for macroscopic gels in some rare cases. But for basically all microgels, the original description in the Flory-Huggins theory was never a good approximation and could not be used. And people used a lot of other possibilities like series expansions and so on for the chi parameter. However, the series expansions have a disadvantage, and this is that they contain unphysical parameters, and it's just a parameterization. So we came up within a collaboration with Nadia with a new idea describing this Flory-Huggins interaction parameter. And Sergei Kakoi in my group, he's a theoretical physicist. He modeled the chi parameter in this way. And the interesting thing here is that we have a parameter nu, and this is in fact the number of water molecules which are cooperatively liberated when the network is collapsing. And so in fact we can fit the swelling curves with this equation or with this chi parameter in the Flory-Reyna theory, and can calculate the number of water molecules which are liberated. And the outcome was in good agreement with MD simulations, and this is how the data look like. So here we have the homopolymer system for the 3 monomers I've already shown before, and you see the swelling curves, radius over temperature, and you see the nice fit obtained with this new approach which we have developed. This also works for copolymer systems, and we can fit basically all molar ratios when we copolymerize these 3 monomers. And at the moment we are working on an extension also including charged comonomers, but this is still ongoing work. Okay, so in fact this idea of using cooperativity works pretty good. And here are the new values we get. So in fact we get between 8 and 15 water molecules which are liberated upon collapsing this copolymer system. And this is a NiPEM copolymer system, and here you have NiPEM and NPEM. And these numbers are in rather good agreement with MD simulations, as I told you already. And moreover, the trend you see here is in agreement with the hydrophilicity or hydrophobicity of the used comonomer. Okay. So let's come to some possible applications. One possible application is drug delivery, where you use this collapse transition to release drugs at a certain temperature. Or you can use such particles as carriers for nanoparticles, embedded palladium or silver or gold nanoparticles. The microgel prevents them from aggregation and from precipitation. And you can, in addition, use the volume phase transition temperature to regulate the catalytic activity. The first works in this area were done by the group of Matthias Ballauf and Jan Lu. And meanwhile, a lot of groups are still working on this catalysis topic. Another application is the use of these materials as photonic materials, or you can use them as surface coatings for cell culture substrates. And I will come back to this later. First of all, I would like to show you some recent work from my group on catalysis. And here we have embedded palladium nanoparticles in methacrylic acid copolymer systems with poly-NN-PEM. And the methacrylic acid is used for binding the nanoparticles and keeping them in the network. So we can also make core shell structures like shown here, where you have the nanoparticles in the core. The core contains methacrylic acid, and then you put a shell on top of this by a second precipitation polymerization step. And the particles you get look like this. So you have the nanoparticles inside the microgels, and the grayish things here are the microgels. And the interesting thing about it is, of course, first of all, that you can stabilize the nanoparticles, but second, that you can regulate the catalytic activity. So this plot here shows the logarithm of the rate constant determined at different temperatures. So this is the inverse temperature. And on the right, you see the hydrodynamic radius of the used carrier particle. And you see the radius goes down with increasing temperature. And at the point where the collapse occurs, also the reaction rate goes down. So this can be used to downregulate the activity of the nanoparticles which were incorporated in the present microgel. And you can, from the linear slope here, you can, in addition, of course, get the activation energy. This is Arrhenius-like behavior, and here we have a strong deviation from Arrhenius-like behavior due to this collapse of the particles. This can also be used for, I've forgotten to mention that in this case, we have used the reduction of nitrophenol, because this can easily be followed by UV vis spectroscopy. And as reducing agent, we have used sodium borohydride. But you can also catalyze more complex reactions. And an example is shown here. This was a collaboration with organic chemistry here in Bielefeld, Norbert Seewald. And we can use our catalysts also for the Suzuki-Miyaura cross-coupling reaction. And the product is rather complex materials which are interesting for pharmaceutics. And this also nicely works. Here are the particles we have used. Here we have rather big nanoparticles which were obtained by reduction inside the microgel. And when we use a different microgel containing dimethylamino-propyl methacrylamide, we get very, very small nanoparticles in a very big surface area. And this is also, of course, interesting for the reaction rate. And here you see the conversion for this model reaction. And we get quite good conversion also at rather mild conditions, already at 37 degrees Celsius. This shows that these particles can be used in a rather versatile way. And in future work, we plan to incorporate also some enzymes in addition to the nanoparticles, and this would allow to have a kind of compartmentalized system where you have a biocatalysis jointly with metal catalysis, which is usually impossible when you have just both partners or both catalysts in the same volume. The metal would, in this case, denature the protein. So by having such a carrier particle, you can really think about new reaction cascades. Now I would like to show you briefly what we also can do with these particles. So we can take the microgel solutions, we can spin coat them, and then we get monolayers covering a surface. The surface can be a cell culture dish, and then we can grow cells on this microgel surface. We grow the cells at 37 degrees. This is an example with mouse fibroblasts, and you see that they nicely adhere. This is visible by these bright surroundings of the cells in this contrast enhanced microscopy. And then we lower the temperature. The temperature is lowered. That means the microgels, which are below the cells, swell and the cells start to round, and then you can just easily rinse them off. And this is not an easy task for mammal cells usually, because they stick to the surface and they have anchors which are really grabbing the surface, and in biochemistry you usually would have to use trypsin or other proteases to cut these anchors off, and this will kill at least half of the cells. So if you want to harvest the cells for purposes of analytics or whatsoever, it is of course much better when you just can rinse them off easily, like we can here in this example, and this is the surface after rinsing. We can also make cell assays with it. So what you see here is a fluidic channel, and in the channel, by microcontact printing, we have generated a circular pattern, and this can be used to remove all cells from this pattern by flushing the channel. And then we have a starting point to measure growth kinetics, and we can follow how the cells come back into this cell-free area. And you can do it with a control sample of the cell line you want to study, and you can do it in presence of some pharmaceutical products, like in this case locostatin, which prevents cell mobility. And we can now look at the growth kinetics. This is the unperturbed growth kinetics, and this is what happens when you have locostatin in the buffer where the cells are grown in. This can, of course, also be used, or we think it can be used for individualized medical assays to check whether a certain patient can reacts, or the tumor from a certain patient reacts on a specific cytostatic. We have also checked this for Chinese hamster ovaries, and here you can also see how these cells go back into the cell-free area. And we checked it for, meanwhile, for a lot of different cell lines, epithelial cells, breast cancer cells, and osteosarcoma cells, myoblasts, and even stem cell lines. And for all these cell lines, this principle of swelling the microgels to remove the samples from the surface perfectly works. Okay, if you want to learn more about microgels in general and about applications and future trends, you can have a look at this review article, which we have recently put together with a lot of people working in the area. Basically, this was the outcome of a symposium at the ACS meeting in New Orleans, which was the last one before Corona. And afterwards, due to Corona, we had a lot of time to write the review. Okay, now let's come to the P-jump experiments. In this case, we have studied NNPEM-based microgels. Here you see the microgels we have investigated. The image you see is a helium-ion microscopy image, giving really nice contrast. And we can, from image analysis, obtain the size distribution. And we have a mean radius of about 200 something nanometers. Here you see now small angle neutron scattering data for these microgels as a function of temperature. And the interesting thing is that we have a very, very sharp transition So yeah, Newton scattering data here is intensity over scattering vector q, or magnitude of the scattering vector q. And at when you go from 22 degrees Celsius to 22.1 degrees Celsius, we see a big shift in the position of this first minimum in the scattering curve. This indicates that the particles within 0.1 Kelvin completely collapse. So this is a very, very sharp transition. The curves were fitted with the polydispersed sphere model. In addition, at high Q in the Swan state, this is the 4 curves here, we have to add a Lorentz contribution for the mesh size, that is the internal structure of the microgel particles. Okay. Very sharp transition. This is probably the sharpest transition ever observed. Now we wanted to study, or we wanted to use these particles to study the response kinetics. And the response kinetics can be studied by stroboscopic pressure jump experiments on a small angle Newton scattering beamline. And this is an image from the D11 beamline at Institut Laue-Langevin. At the moment, it's not in place anymore because they are refurbishing the Newton guides, but this was the installation in 2018 when we did the experiments. And this is the pressure jump device, which was developed by the group of Thomas Sottmann in Stuttgart. And we went to ILL to use this for our pressure jump experiments. But before that, we checked how the reaction of these particles, of these microgels, to pressure is. And this can be done by dynamic light scattering in a pressure cell. So here you see again hydrodynamic radius over temperature. The black curve is the poly-NN pump microgel in light water. And you see a rather sharp transition at about 22, 23 degrees. When we go to heavy water, which we have to do in Newton scattering to have a scattering contrast, we have a slight shift by maybe 2 Kelvin to higher temperatures, but there's still a very sharp transition. And if we now go from 1 bar pressure to 300 bars, we see that the particles, the transition temperature shifts even to much higher temperatures. So in fact, pressure induces particle swelling. And this can be followed because we can now jump between 1 bar and 300 bar, and this drives the particle from shrunken to swollen state and back if we jump back. And this is, of course, interesting if we want to measure the response kinetics of such a particle. Here you see the static scattering curves as a function of scattering vector at 3 different pressures. 50 bar, 100 bar, and 200 bar. And you see, okay, at 100 bar, the particle is still in the shrunken state. At the temperature we used here, this was above 22 degrees. And at 200 bars, it swells. And that moves the form factor minimum to the left. This is a total data set we measured. The interesting point is the time resolution. In fact, we have the first curves already at times of about 2 milliseconds. That's the absolute limit. And to have sufficient statistics, you have to do it in a stroboscopic way. And the detector works in event mode. So the data are stored with timestamp. And you can afterwards average several p-jump measurements. And in fact, to obtain sufficient statistics, we had to average about 5,000 p-jump experiments. But when we do so, we get the following. We have the pressure jumping from 50 bars to about 200 bars, staying at 200 bars and going back again to 50 bars. Approximately. And this, the black dots show how the radius of the particles changes. So the radius goes from about 90 nanometers up to 185, and then goes down again to the shrunken state. So it follows nicely the pressure jump. And what we see now is that we have, in one case, one single exponential. This is the swelling of the particles. So this process here is the swelling, and this can be fitted with a single exponential having a relaxation time of about 1.3 milliseconds. And then we have the two-step collapse. So the collapse is first probably driven by the collapse of dangling polymer change on the surface, which is fast. And then we have a slightly slower collapse to the final shrunken state of the particles. And the response time is, of course, pretty fast. So this shows that such particles can, of course, be used as sensors and maybe also as actuators, but the response time is really fast. Okay, let's now come to the core shell microgels. Core shell microgels, or at least, presumably core shell microgels can be made by making first a core out of one of the shown monomers. In this case, we have used a NiPeMem, which has a transition temperature of about 44-45 degrees Celsius. And then on top, you can precipitate a shell. And the shell is NNPEM, having this LCST of about 21-22 degrees Celsius. The crosslinker of the core was varied in our experiments. The shell always had the same crosslinker content. And the work was a bit inspired by Walter Richtering's works on core shell microgels, but he used NiPeM instead of NNPEM. So here we have a much bigger difference in transition temperatures of the used original polymers. So this is how particles like this look like in SEM. And here you see static light scattering curve. So you can again see this typical form factor oscillation. So intensity versus Q, and you get a form factor oscillation. And you can fit this with a polydispersed sphere model. The polydispersity is found to be about 6% in this case. So this is very typical. You get very monodispersed particles in the precipitation polymerization. Now let's have a look at the swelling behavior of the microgels. This is radius over temperature, and these are the data for NiPeMem core particle, poly-NiPeMem, with 10 more % crosslinker. So this is nothing special, the usual swelling curve you would expect. And now on top we precipitate the shell material, and now the swelling curve changes completely. You have a transition at about 22 degrees. This is NNPEM, but then you get a linear swelling and a very shallow collapse at the end. So this is very different compared to what we had before, and makes these particles interesting because you have a linear response over a wide range, and this can even be really used for nano actuators, or also for as sensing material in an ettalon, where you linearly change the resonance wavelength. This can also be done in the adsorbed state. So here you see bulk measurements in solution, but for the same system we can also make a surface coating, and also the surface coating is found to respond linearly. This was measured by ellipsometry. And here we have on the right side the layer thickness. This is for the red dots, and this is the hydrodynamic diameter for the black dots over temperature. To understand what happens here, we started a collaboration with a group of Julian Oberdisse in Montpellier. And we wanted to understand, in fact, what the real structure is we have, because we thought, of course, it's a core shell structure, but this is a very funny behavior, and we didn't expect it. So we decided to do in detail small angle neutron scattering on these systems. And Julian is an expert for Monte Carlo simulation analysis of scattering curves. The program he developed works like this. So you have the scattering curve, then you make a model, and here the only input we put in is that we have a spherical structure, which is assumed to consist of concentrical shells having different polymer density. And then the Monte Carlo algorithm just moves monomers between the shells then you calculate, based on the new monomer density, you calculate the scattering curve, and then you check whether the description of the experimental data from small angle scattering became better or became worse. And if it becomes better, then you take the new configuration. If it's worse, then you go back to the initial and you make a different Monte Carlo step. And the outcome afterwards is the density of monomers distributed in this concentric model, and you can calculate the density as a function of particle radius. And this is an example for a collapsed particle where you have a steep decrease in density and a little bit of density due to some roughness of the surface. Okay, here I would like to show you how this in fact works. You start with an initial distribution of monomers, and what we model here is a microgel measured at 55 degrees Celsius, small angle scattering curve, I over I of Q versus Q. And this is what happens then. You see the green curve approximates better and better the scattering data, and at a certain point you get a very good description. And you have to repeat this several times with different initial configurations to make sure that you have no artifacts due to the choice of the initial parameters, and then you average about 1,000 simulations to get the final outcome, and this is the final density distribution which is shown here. And of course the green curve represents the final reverse Monte Carlo fit of our data. Now we had a look at deuterated monomers. A NiPeMom can be obtained as a D7 version with 7 hydrogens replaced by deuterium, or also the fully deuterated form is available. And here you see again radius versus temperature, or normalized radius versus temperature for NiPeMom, D7 NiPeMom and D12 NiPeMom. And you see that the deuteration leads to a shift of the transition temperature. So this is the hydrogen-containing monomer. Then we have the yellowish curve, which is the D7, and the D12 lies in between the two. This was unexpected and is still somehow not fully understood, but this is how the data looks like. So if you do a contrast variation by deuteration of monomers, to highlight structures, you have to be aware of the problem that you shift the phase behavior of the system. And but however, qualitatively, the behavior is very similar for all these versions of the NiPeMom. But we need the deuteration to do contrast variation. And what you see here is now core contrast. That means we have a mixture of heavy and light water to highlight the core, the presumably core forming polymer, which was the NiPeMom. And here you see the different density distributions of the NiPeMom monomer at different temperatures. But now we go to an inverted contrast where we match the core and see only the shell polymer. And this gives us the distribution of the shell monomer. And in fact, this is completely unexpected, or this was unexpected, because what we see here is that we have a very high density of the shell monomer, which was supposed to form a shell, inside the core. So in fact, we did not make a core shell system as we thought. This was a typical chemist's idea. So you make a synthesis and you have a collapsed core where you precipitate the shell on top and you get a nice core shell structure. No, it wasn't like this. We have in fact an interpenetrated network which has a very small shell made out of the shell polymer, but nevertheless it's an interpenetrated network. And this can only be shown, I think, by neutron scattering, because only there you have the possibility to do this kind of contrast variation. So this is a summary of the outcome. We have, from our Monte Carlo approach, we can calculate all densities of the two monomers used, And we can also, in addition, calculate the water density. And we have clearly shown that, in fact, we don't have this expected structure, but we have an interpenetrated network structure with a rather thin shell of the second comonomer. So no real core shell structure, but interpenetrating network. And in fact, it's interesting because when instead of poly-NN-PAM for the shell, when we use NIPAM, we don't get this. Then we get really a core shell system. So a small difference in the steric demand due to the different side chain used in this monomer changes largely the properties of the obtained material. To get an additional idea of what is going on, we teamed up with the group of Thomas Huser here in Bielefeld. Thomas, he is an expert for super resolution optical microscopy, and especially for DStorm. DStorm stands for direct stochastic optical reconstruction microscopy, is one of these reconstruction microscopies which were awarded with a Nobel Prize in 2014, I think. And what you see here is, again, our core material, the poly-NIPAM core particles. And this is the hydrodynamic radius over temperature. So again, the swelling curve. And on the right, you see the DStorm images. When we put these particles into a buffer containing rhodamine G6. And now the dye diffuses inside the network. And DStorm is based on fluorescence dye localization. So what we get is, in fact, a localization density, and we localize the dye distribution inside the microgel network. And when you do this for a core shell, here you see it's more or less, you have a slightly higher density in the inner part, and then you'd have a decay of the localization density to the outer part. And here I show you now the results for the poly-NIPAM at poly-NN-PAM core shell, or presumably core shell particles. And you see when we have different crosslinker contents and different amounts of shell material, we get different brightness. And here, you, for example, you clearly see that you have a high fluorescence at the rim, and we get rather low fluorescence inside. And the change here was that we just used more or less of the monomer, so we increased the amount of used poly-NN-PAM. Increasing, shell thickness is maybe not correct, but increasing amount of NN-PAM. And this is, in fact, the localization density of the used dye, rhodamine G6. And here, the interesting part is the right image here, which is the 3D reconstruction of the localization density as a function of radius. And the core only shows this black curve, so we have a decrease of density of the microgels from the interior to the exterior, and this is in good agreement with results from scattering experiments. And when we now look at the core shell system, we see that when we have a thin shell, we have some density of the dye inside, but when we have more shell material, more NN-PAM, we only get a localization at the rim of the particles. And this is due to this interpenetrating network, which we have shown by small angle Newton scattering, because here the dye cannot enter anymore because the internal part of the particles is just too dense, and the dye molecules are too big and they stay to the shell, and this gives you this bright rim here, which you can see in the DStorm images. And the spatial resolution which we achieve with DStorm in this case was about 28 nanometers. So this is approximately 10 times better than the upper limit with normal microscopy, and these data are in very nice agreement with the Newton scattering results. So in fact, yeah, this is the summary of this part, and we have a very dense core due to this interpenetrating network formation. Okay, so let me come to the conclusion, and yeah, I hope I could show you that microgels can be interesting for different applications, for example, for surface coatings, for cell culture media, and also for catalysis. And I hope I could convince you that Newton scattering is of paramount importance for the study of microgel properties, because without Newton scattering, you have it's very, very difficult in such mesoscale systems to find out what the real structure is. In fact, NMR or also other methods have no sufficient resolution and cannot give these results which we obtain with Newton scattering. At the end, I would like to thank basically the people who did the work, members of my group. This is an image from our recent excursion, which we do once a year. And then I will have to thank also the collaborators, which we have over the last years. And I have to thank, of course, the local contacts of the different large-scale facilities, especially, of course, Meyer-Leibniz Center in Munich. And yeah, we did also some experiments at LLB in 2018. Unfortunately, now LLB has been shut down, and we still do, of course, a lot of experiments at Institut Laurent-Langevin in Grenoble. And at the end, I have to thank the French and the German taxpayers, because parts of the work is funded in a French-German project, which is paid by Agence Nationale de la Recherche and jointly by Deutsche Forschungsgemeinschaft. And we got some direct funding from the Ministry of Research in Germany for instrumental developments. And I thank you for your attention, and I'm yeah, curious to listen to your questions and to try to answer them.
Thank you, Professor Helweg. So let us start. We have some minutes for some questions, and I'd like to know if you are working also with your other responsibilities, like external fields or maybe pH. We saw some pH dependencies.
Yeah.
Could you tell us about?
Yeah, I didn't talk about it, but of course we also use, for example, acrylic acid as a co-monomer or methacrylic acid. And if you incorporate, let's say, 2 or 3% of such organic acids, then the particles become pH responsive. And this can also be exploited if you think about sensoric applications. You can, of course, also incorporate cross-linkers, which can be cleaved by light, which would make the particles light responsive. But in this case, it's of course not reversible. The carboxylic acid containing systems are of course also sensitive with respect to ionic strength. And I don't know, maybe you know the works by Michael Zerpe from Canada. He is using microgel monolayers for etallons. So he coats on a gold-coated glass slide. He coats the microgels. On top, he sputters additional gold, and this gives you an etallon, which can change the resonance condition as a function of pH, for example. Or they also detect other species like sugar, so you can use it for glucose detection in the bloodstream and things like that. So, and then there's a lot of work which has been done by this group for other stimuli, like for example, glucose detection and so on.
Okay, thank you. We have some questions for audience, and one is from Joyce Scheibel.
Oh, okay. Yeah.
So she's talking about the Penempam microgels, because they have a sharp transition in Q vector in small difference of temperature, but so here's the question, if you could answer it.
Yeah, I can try. Okay, let me go to this. You're talking about this scattering curve, isn't it?
I think so.
Yeah, okay. So the question is why it's so sharp, or
About the sensibility of the sun's apparatus for the temperature, but
okay. Yeah, here this was the temperature precision was about 0.1 K. So it's about 0.1 Kelvin.
okay, it's a nice result.
Thanks.
And Professor Helveg, your systems are mostly based on PENIPAN or related polymers, and maybe the examples you gave us here, but there is other classes of microgels with similar properties using sustainable polymers. Let us say sustainable.
Yeah, in fact, you can also try to use other systems. The question whether it's really sustainable or not is, I mean, in fact, basically, I still think that most of the monomers are made by petrochemical approaches. But of course, you could also try to make them from bio-based synthesis, or at least parts of them. I mean, there are many processes where you can make organic material using some pathogens, which can produce, for example, alcohols based on syngas approaches. In fact, I mean, we did not care too much about sustainability, but the work we have done together, this was, of course, an idea to have starch
Yes.
inside the microgels, and then we have polymerized the napalm on top of the starch, so you can make bio polymer hybrid systems, which can also be interesting for some applications. So in fact, it's possible. I mean, there's still a lot of things you can do, and at present we are looking for monomers having a phase transition at much higher temperature, at 80 or 90 degrees. And there it's not quite clear yet what kind of monomers we will use. But in fact, I mean, you use always amides, and of course the acids you can certainly get from plants or from other renewable resources. So I think it's just a matter of synthesis of the monomers, but in fact afterwards it's you can make whatever microgel you want.
Thank you. So you show us nice examples using chemistry and colloidal systems, thermoresponsive microgels, but to characterize, you are showing us that it's very important to do neutron scattering experiments. So in fact, we don't have neutron scattering in South America. So my
Yeah.
question is about it. We could apply for neutron scattering experiments at ELL or in other
Mm,
facilities.
ELL, I don't know. It's I know how it works at ILL. At ILL, you have first of all three so-called associates. They pay about 80% of the bill, which is Germany, France, and Great Britain. And then there are something like 12 scientific partners, and they pay the rest. And if you are not from one of the partner countries or from the associates, then you have to team up with people in a real collaboration. which are from the partner countries or from the associates. So if you would, for example, if you have an idea for an interesting project, you could ask someone from France, and you could do the experiment jointly with this group. This is how ILL works. In Munich, it's different. You can apply. Everybody is allowed to apply for beam time. There is no restriction, at least not yet, from a point of view of nationality. It's just beam time is just granted on the basis of scientific excellence. The problem with Munich is at the moment the reactor is unfortunately down and will not restart before the end of 1924. And at full scale at the end of 1925, because there was a problem with the main channel, which where the fuel element is hosted, and this was broken. So it's just a bit of a mess at the moment in Germany, because this was our last reactor source. Before we had 5 reactor sources, and now we are down to Munich, and there's one more very small reactor source in Mainz. But this is only used for high energy physics.
Okay. And just one last question, because people in the audience are working in our graduation programs, students, let's say that, and they are interested in the possibilities to stay in your lab. So if it's possible, I think that our student Joyce Scheibel is going to stay with you a little bit, maybe 6 months, but it's possible for you to receive other students from Brazil?
Of course. It's the only problem is, of course, funding. So one has to look for funding. In Brazil, or you can also apply for grants from DAAD, the German Academic Exchange Service. They can even, sometimes they finance entire PhD thesis projects. But of course, you need a host. The host has to declare that you get lab space and office space and so on. But that's no problem. We would be happy to host people. The question is how to finance this. We can provide lab space, chemicals, instruments. We can also provide some travel money, but that's basically it usually. And the rest has to be found somewhere else. So if you have funding sources in Brazil, you can apply for them, but you can also try to get a grant from a German Academic Exchange Service, DAAD. Yeah. And I think they have an English-speaking webpage. And there are sometimes calls, joint calls with the Brazilian funding agency. And but I don't know the deadlines at the moment. If there are some upcoming deadlines, no idea.
Well, that's we have a lot of different sources. So let us inform the students here how to do that, and we can keep in touch.
Yeah.
So, Professor Helweg, we would like to thank you for this nice presentation and the interesting subject for soft matter and nanoscience. And we can finish here, hoping that you are thinking to visit us in the near future, maybe.
I hope so, yeah.
Yes, and we can try to expand the collaborations, and you can know a little bit Brazil, or our university, but also our synchrotron facility. So thank you very much.
You are welcome. It was a pleasure.
Yeah, thank you.